Hello, everyone. My name is Vaibhav Singh. I'm a machine learning specialist working with Google Cloud. And here is,
I'm Taylan Bilal. I'm a software engineer in Google Cloud working on Pytorch on TPUs.
and today we are going to talk about PyTorch at scale on Cloud TPUs. So let's get started. And here is going to be our map for the talk. We're going to start with an introduction. Then we'll move to step-by-step walkthrough of an example. We will discuss how it exactly works and how to scale your PyTorch training on Cloud TPUs. And finally, we are going to leave you with resources, tips, and tricks so that you can start to train your PyTorch model on TPUs today. PyTorch is officially supported on Cloud TPUs. This support is made possible through the Torch Xla library, an open source initiative from Facebook and Google. It was announced in October 2019 at PyTorch DevCon and has been growing ever since. The support reached beta with PyTorch 1.5 release and would be generally available by the time you'll be seeing this recording. For those of you who are not very familiar with TPUs, TPUs or Tensor Processing Unit is a hardware accelerator built by Google in 2015. First, to address its own internal needs, the very first generation of TPUs was an inference-only chip. Beginning with version 2, it evolved to support training as well. And beginning with version 2, Google also made TPUs available to the rest of the world through Google Cloud, with the vision to help push machine learning state of the art forward. You can scale your machine learning workloads using TPUs from 8 cores all the way to TPU pods. TPU pods consist of thousands of TPU cores. As you can see on the left-hand side of your screen, TPU comes in two different flavors on Google Cloud as of today, that is TPU v2 and v3. You can start with a device, as you can see on the left-hand top corner of your screen, all the way to the full pod. A Cloud TPU v2 pod comes with 512 cores, and a Cloud TPU v3 pod comes with 2048 cores. You can choose a slice of a pod all the way to the full pod for your machine learning trainings. Here is a Cloud TPU device. In order to access this device, a user creates a VM or a virtual machine on Google Cloud and creates an instance of Cloud TPU. You can create this instance in different device types. In this case, we are choosing v3.8. That indicates a v3 device. Each v3.8 comes with 4 chips. Each of these chips has got 2 cores, and each of these cores come equipped with matrix multiplication units, 2 matrix multiplication units each, and 16 GB of high bandwidth memory per core. All in all, this device has got 8 cores, and that's why when you choose the accelerator type when you're creating this device, you choose v3.8 or v2.8. Whereas when you're working with pod, in case of a Cloud TPU v3, a full TPU pod consists of 256 TPU devices or 2048 cores interconnected with a high-speed interconnect, which lets the gradient averaging or all reduce operation run very efficiently on the full pod. The TPU software stack enables you to train all the way from a TPU device to the TPU pod or any intermediate size without any code changes. And it always acts as a single node without any complicated cluster setup. Now, let's take a look into an example of a PyTorch code as we know it, and then see how this code needs to be modified, or what are the modifications we typically see in order to run that PyTorch code on Cloud TPUs. So first of all, let's begin with a familiar territory. For those of you who are familiar with distributed training on PyTorch, you have already seen similar examples, similar elements such as the PyTorch distributed library. You see the model, you see the model being transferred to the devices, in this case, GPU devices. You see the familiar elements like data loader and distributed sampler. The distributed sampler makes sure that each of the replicas of the model are actually looking at the different slices of the data and not looking at the same slice. You see familiar elements like the train data loader. You see the forward pass within the training loop and the backward pass, which computes the gradient. You see the optimizer step. that is going to update the parameter based on the computer gradient and the optimizer of choice. And you notice the torch multiprocessing spawn method, which executes this training loop. In this particular example, 4 different replicas of this model running in parallel. Now let's see how this code changes when we are going to train it on Cloud TPU device. As I was describing, a Cloud TPU device consists of 4 Cloud TPU chips or 8 TPU cores, beginning with the elements like Torch Xla library. This is what makes the training of PyTorch model on TPU possible. Similar to what you saw in case of GPU, we have another device abstraction called Xla device. This is an abstraction of Cloud TPU core, similar to how you were transferring your model on Cloud TPU device. You are transferring your uh, model on Cloud TPU core here. And finally, the elements like the distributed sampler or the data loader remain exactly the same, with one difference that we are using a parallel loader, which is a wrapper here that makes sure that the data upload operations to TPUs are run in parallel with the computations in order to make the data pipeline efficient. One more important distinction to highlight here is that we are using the optimizer step method from XLA module instead of optimizer dot step method that you saw in the previous example. This is to make sure that the all reduce operation is performed first before the optimizer dot step is called to update the parameters. And finally, instead of the Torch multiprocessing module, you have XLA multiprocessing module, which has the similar spawn method, which under the hood takes care of all the necessary TPU device initialization and setup before using the Torch multiprocessing module to start again in a similar fashion. The processes running in parallel to facilitate that training on 8 different replica of your model in this case, because we are running on 8 cores. And also notice the start method equal to fork, which is used to make sure that the model is copied into the memory only once. Each of the child process will be able to use all the resources are spun up before that in the global scope. Now let's look at the live example of one of the trainings that we are going to do on ResNet 18 model using the CIFAR 10 dataset. So we start with a Cloud Console. Here I have set up a Cloud AI Platform notebook instance with Pytorch Xla library and all the necessary components ready to go. So I start my notebook instance. In the meantime, notice also that I have created a Cloud TPU instance. That's a B38 device, so 4 chips, 8 cores. Notice the runtime version that is displayed in this column whenever you create a Cloud TPU device, and this is the internal IP that is used to set up XRT TPU config environment variable before you start the training. This is required for the user VM or your VM to be able to communicate to the TPU instance. So we are about to demo the Pytorch ResNet 18 model on CIFAR 10 dataset. So as described earlier, we start by setting the XRT TPU config environment variable. This is the IP address that we noted earlier. So we execute this cell, then define some hyperparameters, then sourcing the libraries there. Notice that here we are using the ResNet 18 model from Torch Vision library. Then we define our training loop. Notice in the training loop that apart from the test loop function, apart from the train loop function that we have seen in example walkthrough there, we also have the test loop function defined for tracking the evaluation metric and the results. Rest of the aspect of the code should look very familiar to you based on the walkthrough. Here is the helper function for plotting the results. And this is the function that is going to call the training method, which will have the training loop function that we saw above. We're using the XLA multiprocessing spawn method here, and we are using the MP function as one of the argument and passing the other flags, specifying the number of cores, and start method fork as described in the walkthrough. And then here we start. So as this training is starting to run, we are going to look at another instance of this notebook, which has this whole training execution finished. And as you would notice that we execute this training for 20 epochs, so it is going to take a few minutes to finish. After 20 epochs, it attains close to 78-79% of accuracy. And you can also notice that it is possible to track things like images per second and other metrics as you would do in a normal Pytorch code. So here we are getting almost 76% of the accuracy, and then here we are ready to visualize the results. And these are the results here. As you can see that for most of the examples, it was still working well, and there are some error cases as well, since it only attained about 76% of accuracy. Now that you're familiar with Torch XLA usage, you may be wondering how exactly it works. If you're familiar with Pytorch Tensor class or A10, you already know that it extends support to multiple device implementations or memory layout through dynamic dispatches to those implementations. Torch XLA extends A10 with a new type of tensor called XLA tensor. XLA tensor is different from other eager implementations in that it's a lazy tensor. While eager tensors are dispatched op by op, and the only computation graph that is generated is for the gradient computation, and as soon as the gradient computation or the backward pass is done, this graph is destroyed. The lazy tensor, in case of lazy tensor, Pytorch XLA just constructs an XLA intermediate representation graph with no evaluation is performed on this graph until required, either by a certain operation in your model code itself or by a call that necessitates the context transfer from the tensor to scalar. Building this IO graph also enables Pytorch XLA to do certain graph level optimizations, which are not possible if you are doing the op by op dispatch. This IR graph is then sent to TPU device, is then compiled and sent to TPU device for execution. Between training steps, if the IR graphs are identical, XLA compilation is not performed. However, if IR graph is going to change too frequently between training step or because of the nature of the code itself, every time it changes, the XLA compilation needs to be performed, and it might slow down your training. To take more details into what are the things to watch out for and how you can make the most of your PyTorch training, here is my colleague Taylan, who would talk about tips and tricks.
All right, thanks, Vaibhav. So let me talk about some of the tips and tricks, things to watch out for when you port your model from GPU code to TPU code. One of the most common pitfalls is dynamic input shapes. As Vaibhav noted earlier, every time the intermediate representation graph changes, this triggers an XLA recompilation. And that slows things down. And this happens when the model has input shapes that change from one step to another. A good example is an NLP model where you have sentences of varying length, for example, or an image model with images changing shapes. Another common pitfall is what we call a context change between device to CPU. And the most common occurrence for that is when the code has tensor.item calls in it. This slows things down because, as Vaibhav noted earlier, XLA is built on a lazy tensor idea, and the item calls prematurely causes evaluation. and result is suboptimal if that happens. Third most common pitfall is if the model code is using some operation that has no XLA implementation yet, then that doesn't cause an error, but it causes the IR graph to get cut, and the operation that's not lowered to XLA gets executed on the CPU, which slows things down. We want to stay in the device context as much as possible. When that happens, these things happen, we have solutions. For example, for the first problem, dynamic input shapes, we may use padding. We may take the sentences with varying length and pad it to a fixed length. Or maybe we predetermine 3 or 4 fixed lengths and pad it to the next length. And in the latter case, we will still have recompilations because the input shapes will take 3 or 4 different values. And each time, the first time they are seen, we're going to compile. But we're going to waste less flops as a result of less padding. So there's a trade-off there. Second, when we have the tensor to scalar context change or device to CPU context change, this can happen because of, for example, loss reporting, because loss is usually a tensor. What we do, we recommend to reduce the item calls and report loss every n steps instead of maybe every step. N can take a value of 20, 30, 100. That's up to the user. The user could also have item calls from another part of the model. They need to be spotted and eliminated. In the third case, if we encounter an op with no XLA lowering, we usually just create a GitHub issue in Pytorch, github.com/pytorch/xla, and ask the Torch Xla team to lower the said op so that the operation runs on the device and is accelerated as a result. We have talked about problems and solutions, but how do you actually understand what is going on and what the problem actually is? So this is the slide from earlier. We want to focus on the white rectangles here. We are importing Torch Xla debug metrics here, and we are printing the metrics report. This metrics report contains a lot of information about what's going on at the XLA level, and it can surface some of the issues that I just discussed in the previous slides. And let's look at an examples metrics report. This is just a summary that focuses on the issues that we discussed. The actual metrics report contains more information than just this. If you look at the first part, the metric compile time, this gives us information about how many graph recompilations have occurred in this workload. And in this case, we have 202 compilations that occurred. And the total time it took is 6 minutes. Now, the metrics report is usually composed of metrics and the counters. The counters give information about what's happening in the code. For example, the counter mark step tells you that how many training steps that we have taken. For example, in this case, 232 steps have been taken, and that resulted in 202 compilations, which suggests that there's a problem with the graphs that the code is generating. The compilations should be at low. Some compilations initially are okay, but it shouldn't grow as the number of steps grow. Similarly, for example, in the item call problem, the context switch between device and CPU, the counter A10 local scalar dense will be your friend. And here in this case, you have 240 occurrences of that, and that's something that needs to be reduced to get optimal performance. In the third problem that we discussed, the op that's not been lowered yet, you will see an A10 counter with the op's actual name. And in this case, we have 232, probably once per step, that some op that needs to be lower in XLA. And once you iron those issues out, the code will run much faster and will be very performant. Now, so far we have seen how training works on a Cloud TP device. Now let's discuss how to take it to the next level and train on a Cloud TP pod. As pods were described by Vaibhav earlier, they consist of several devices connected with very fast network. And in the Pytorch Xla context, we create as many user VMs as the Cloud TPU devices, not cores. So for example, if you want to train on a V332, 32 cores, we would need to create 4 VMs to drive the training. And we wrap these user VMs in an instance group. So everything needs to be in an instance group. And once we have set up these resources, launching the training distributed mode is very easy. Now let's look at the command to do that. Here, the white part of the large command is the actual command that you are running to run on one device. So this is your code with arguments. And all you need to do to scale it up to a pod level is just prefix the command with these elements. And here, the green part is XLA dist. It's offered by Torch Xla, and it coordinates the resources, sets up the mesh between the instance group and the TPUs, and sets up the environment variables specified by the next set of elements. For example, the TPU name, the conda environment, and any other environment variable that you might want to set up. And that's it. There's really no code changes. One gotcha here is the code needs to be written so that the data is sharded across all the cores. Otherwise, the VMs will end up doing the same work, unnecessary work. But that's really the only gotcha, and scaling up is as easy as just prefixing your command. So now let's look at some of the models that actually have been tested and known to work. In the computer vision area, we have ResNet and ResNex, and along with most torch vision models such as MobileNet and others that already work. In the NLP area, we have transformers that work. For example, FairSeek's transformer, Roberta, or Hugging Face's transformers. We have a working implementation of a deep convolutional GAN that's up on our GitHub. And in the speech recognition world, we have worked with FairSeek's Wave2Vec and vector quantized Wave2Vec. Let me note here that the models that work on Torch Xla aren't limited to these. These have been tested, but people have run other workloads and other models successfully as well. And you can port your model as well. To get started, here are some resources. So these are some of the tutorials that are offered on Google Cloud web pages. And it covers some of the models that I just discussed in the previous slide. And along with the Google Cloud tutorials, there are Kaggle kernels from some of the Kaggle experts in the community that they have successfully run competitions on Torch Xla, and they offer their kernels to the users. And finally, here's a summary slide of all the resources that we saw. Some of the GitHub repositories that are relevant to the project, official tutorials, Kaggle kernels. And please visit Pytorch Xla. It's a very active open source library, and open issues if you encounter any issues, etc. Thanks for listening.